Sir Isaac Newton, a comprehensive biography. Isaac Newton, often considered one of the greatest scientists of all time, Newton formulated the laws of motion and universal gravitation, which laid the foundation for classical mechanics. His work in optics and mathematics, particularly the development of calculus, has had a lasting impact on various scientific disciplines. Sir Isaac Newton was born on January 4, 1643, in Woolsthorpe, Lincolnshire, England. He was born prematurely and was not expected to survive. His father, also named Isaac Newton, had died 3 months before his birth. When Newton was 3 years old, his mother, Hannah Ascough Newton, remarried and moved to live with her new husband, leaving young Isaac in the care of his maternal grandmother. This early separation from his mother had a profound impact on Newton's emotional development. Newton attended the King's School in Grantham, where he showed an early interest in mechanics and mathematics. In 1661, he enrolled at Trinity College, Cambridge, where he initially studied a classical curriculum, but soon became fascinated by the works of modern philosophers and scientists, such as Descartes and Galileo Galilei. During his time at Cambridge, Newton began formulating his theories on calculus, optics, and the laws of motion. Scientific achievements. Newton's most significant contributions to science came during his time at Cambridge and his subsequent years of research. In 1665, when the Great Plague forced Cambridge to close, Newton returned to Woolsthorpe and embarked on a period of intense intellectual activity. During this time, he developed the foundations of calculus, formulated his theories on the nature of light and color, and began his work on the laws of motion and universal gravitation. In 1687, Newton published his seminal work, Philosophiæ Naturalis Principia, Mathematica, Mathematical Principles of Natural Philosophy, commonly known as the Principia. In this work, he outlined his 3 laws of motion and the law of universal gravitation, which provided a comprehensive framework for understanding the motion of objects both on Earth and in the heavens. The Principia is considered one of the most important works in the history of science and laid the foundation for classical mechanics. Newton also made significant contributions to the field of optics. He conducted experiments with prisms and demonstrated that white light is composed of a spectrum of colors. His work in this area led to the publication of Opticks in 1704, which detailed his experiments and theories on the nature of light and color. Newton's contributions to mathematics, particularly his development of calculus, were also groundbreaking. Although his work in this area was initially overshadowed by a dispute with the German mathematician Gottfried Wilhelm Leibniz over the invention of calculus, later life and legacy. In addition to his scientific achievements, Newton held several important positions throughout his career. He served as the Lucasian Professor of Mathematics at Cambridge from 1669 to 1702. In 1696, he was appointed Warden of the Royal Mint, and in 1699, he became Master of the Mint, a position he held until his death. Newton was also elected President of the Royal Society in 1703, a position he held for 24 years. Newton's later years were marked by his involvement in various scientific and political controversies, including his disputes with Robert Hooke and Leibniz. Despite these conflicts, his contributions to science remained unparalleled. Newton was knighted by Queen Anne in 1705, becoming Sir Isaac Newton. Sir Isaac Newton passed away on March 31, 1727, and was buried in Westminster Abbey. His legacy as one of the greatest scientists in history endures to this day. Newton's work laid the foundation for modern physics and mathematics, and his discoveries continue to influence scientific thought and research. His contributions to our understanding of the natural world have earned him a place among the most revered figures in the history of science. Isaac Newton's greatest achievement. Sir Isaac Newton, one of the most influential scientists in history, made numerous contributions to various fields, including mathematics, physics, and astronomy. Among his many accomplishments, his formulation of the laws of motion and universal gravitation stands out as his greatest achievement. This groundbreaking work, published in his seminal book Philosophiæ Naturalis Principia, Mathematica, Mathematical Principles of Natural Philosophy, commonly known as the Principia, revolutionized our understanding of the physical world and laid the foundation for classical mechanics. This essay explores the significance of Newton's laws of motion and universal gravitation, highlighting their impact on science and their enduring legacy. The laws of motion. Newton's three laws of motion, presented in the Principia in 1687, provided a comprehensive framework for understanding the behavior of objects in motion. These laws can be summarized as follows. First law, law of inertia. An object at rest will remain at rest, and an object in motion will continue in a straight line with constant speed unless acted upon by an external force. Second law, law of acceleration. The acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. This relationship is expressed by the equation F equals ma, where F is the net force, m is the mass of the object, and a is its acceleration. Third law, action and reaction. For every action there is an equal and opposite reaction. These laws provided a clear and concise description of the fundamental principles governing the motion of objects. They challenged the prevailing Aristotelian view that objects required a continuous application of force to maintain motion, and instead established that motion was a natural state. Newton's laws of motion have since become foundational concepts in physics, applied in various fields such as engineering, astronomy, and everyday mechanics. Universal gravitation. In addition to his laws of motion, Newton's law of universal gravitation was a monumental achievement that transformed our understanding of the forces governing the universe. Newton proposed that every mass exerts an attractive force on every other mass, and the magnitude of this force is directly proportional to the product of their masses, and inversely proportional to the square of the distance between them. This relationship is expressed by the equation F equals G. Frac m underscore 1 meter underscore 2. R. A. Where F is the gravitational force, G is the gravitational constant. M underscore 1 and M underscore 2 are the masses of the two objects, and R is the distance between their centers of mass. Newton's law of universal gravitation provided a unified explanation for both terrestrial and celestial phenomena. It explained why objects fall to the ground, why the planets orbit the sun, and why the moon orbits the Earth. This law was instrumental in confirming the heliocentric model of the solar system and provided a mathematical basis for Kepler's laws of planetary motion. Newton's formulation of the laws of motion and universal gravitation had a profound and lasting impact on science. His work laid the foundation for classical mechanics, which remained the dominant framework for understanding the physical world for over 2 centuries, until the advent of quantum mechanics and general relativity in the 20th century. Newton's principles continue to be used in various fields, from engineering and aerospace to everyday applications, such as calculating the trajectory of a projectile. The Principia itself is considered one of the most important scientific works ever published. It not only established Newton's reputation as a leading scientist, but also set a new standard for scientific rigor and methodology. Newton's ability to synthesize observational data, mathematical reasoning, and theoretical insights in a coherent and comprehensive manner has inspired generations of scientists and researchers. Isaac Newton's greatest achievement, his formulation of the laws of motion and universal gravitation, revolutionized our understanding of the physical world and laid the foundation for classical mechanics. His work provided a unified explanation for a wide range of phenomena, from the motion of falling objects to the orbits of planets. The impact of Newton's discoveries extends far beyond his time, shaping the course of scientific thought and continuing to influence modern science and technology. Newton's legacy as one of the greatest scientists in history is a testament to the enduring power and relevance of his groundbreaking work. A world without Isaac Newton's discoveries. Imagining life without the laws of motion and universal gravitation. Isaac Newton's contributions to science, particularly his formulation of the laws of motion and universal gravitation, have profoundly shaped our understanding of the physical world. These groundbreaking discoveries, published in his seminal work Philosophiæ, Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, laid the foundation for classical mechanics and revolutionized the fields of physics, astronomy, and engineering. Imagining a world without Newton's discoveries allows us to explore how different our scientific knowledge, technological advancements, and daily lives might be today. Impact on scientific progress and technology. Without Newton's laws of motion and universal gravitation, the development of classical mechanics would have been significantly delayed, or might have taken an entirely different path. The absence of these fundamental principles would have hindered our ability to accurately describe and predict the motion of objects, both on Earth and in space. This lack of understanding would have had far-reaching consequences for various scientific fields and technological advancements. In the realm of physics, the absence of Newton's laws would have left a void in our understanding of the forces governing the universe. Scientists might have struggled to develop alternative theories to explain phenomena, such as the motion of celestial bodies, the behavior of falling objects, and the dynamics of mechanical systems. This would have slowed the progress of scientific discoveries and innovations, potentially delaying the development of important technologies. Technological advancements in engineering, aerospace, and transportation would have been particularly affected. The principles of classical mechanics are essential for designing and constructing machines, vehicles, and structures. Without Newton's contributions, engineers might have faced significant challenges in developing reliable and efficient technologies, from the steam engine to modern automobiles and aircraft. The exploration of space, including the development of rockets and satellites, would have been especially difficult without a clear understanding of the principles of motion and gravity. Impact on astronomy and cosmology. Newton's law of universal gravitation provided a unified explanation for both terrestrial and celestial phenomena, transforming our understanding of the cosmos. Without this discovery, our knowledge of astronomy and cosmology would have been significantly limited. The heliocentric model of the solar system, which places the Sun at the center with planets orbiting around it, might not have been widely accepted or understood. The absence of Newton's law of gravitation would have hindered our ability to explain the orbits of planets, the motion of comets, and the behavior of tides. This lack of understanding could have delayed the acceptance of Kepler's laws of planetary motion and impeded the progress of astronomical research. Our ability to predict celestial events, such as solar and lunar eclipses, would have been compromised, affecting navigation, timekeeping, and scientific exploration. Impact on education and everyday life. Newton's contributions to science have become foundational concepts taught in physics curricula around the world. Without his discoveries, the education of future scientists and engineers would have been fundamentally different. The principles of motion and gravity are integral to understanding a wide range of phenomena, from the mechanics of everyday objects to the behavior of complex systems. The absence of these principles would have limited our ability to teach and comprehend the natural world. In everyday life, the absence of Newton's laws might have had subtle but significant impacts. Our understanding of basic concepts such as force, acceleration, and momentum would have been incomplete, affecting everything from sports to transportation. The design and construction of buildings, bridges, and other infrastructure would have been less precise and reliable, potentially leading to safety and efficiency issues. Isaac Newton's discoveries in the laws of motion and universal gravitation have had a profound and lasting impact on our understanding of the physical world and the development of modern science and technology. Imagining a world without these discoveries highlights the importance of Newton's contributions and the transformative effect they have had on scientific progress and everyday life. Newton's work laid the foundation for classical mechanics and provided a framework that continues to influence and inspire researchers, educators, and innovators across the globe. His legacy as one of the greatest scientists in history remains a testament to the enduring power and relevance of his groundbreaking work. Sir Isaac Newton received several prestigious honors and positions throughout his lifetime, reflecting his immense contributions to science and mathematics. Here are some of the notable awards and honors he received. 1. Fellow of Trinity College in 1667, Newton was elected a Fellow of Trinity College, Cambridge, recognizing his academic achievements and potential. 2. Lucasian Professor of Mathematics in 1669. At the age of 27, Newton was appointed the Lucasian Professor of Mathematics at Cambridge, one of the most prestigious academic positions in the world. He held this position until 1701. 3. Fellow of the Royal Society in 1672, Newton was admitted to the Royal Society, an esteemed scientific academy founded in the 1660s. He later became the president of the Royal Society in 1703 and held the position until his death in 1727. 4. Foreign Associate of the French Royale des Sciences. In 1699, Newton was elected as a Foreign Associate of the French Royale des Sciences, recognizing his contributions to science on an international level. 5. Knighted by Queen Anne. In 1705, Newton was knighted by Queen Anne, becoming Sir Isaac Newton. This honor was a recognition of his contributions to science and his service to the nation. 6. Master of the Royal Mint in 1696, Newton was appointed Warden of the Royal Mint, and in 1699 he became the Master of the Royal Mint. He held this position until his death, overseeing the nation's coinage and implementing important reforms. 7. Burial in Westminster Abbey. After his death in 1727, Newton was honored with interment in Westminster Abbey, a rare distinction for a scientist. This honor reflected the high regard in which he was held by his contemporaries and his lasting legacy. These awards and honors highlight Newton's significant impact on the scientific community and his enduring contributions to our understanding of the natural world. Isaac Newton's family history. Sir Isaac Newton, one of the most influential scientists in history, is renowned for his groundbreaking contributions to mathematics, physics, and astronomy. However, his personal life and family background are less well known. This essay delves into the family of Isaac Newton, exploring his early life, relationships with family members, and the impact of his family dynamics on his career and achievements. Isaac Newton was born on January 4, 1643, in Woolsthorpe, Lincolnshire, England. He was the only son of Isaac Newton Sr., a prosperous farmer who died 3 months before Isaac's birth. His mother, Hannah Ascough Newton, was left to raise young Isaac on her own. Born prematurely and not expected to survive, Isaac's early life was fraught with challenges. The absence of his father, and the subsequent remarriage of his mother, profoundly influenced his upbringing. When Isaac was 3 years old, his mother remarried Barnabas Smith, a wealthy clergyman from North Witham. Hannah moved to live with her new husband, leaving young Isaac in the care of his maternal grandmother, Marjorie Ascough. This separation from his mother was a significant emotional event for Newton, and he later expressed feelings of abandonment and resentment towards his mother. Newton's relationship with his mother remained strained throughout his life. Despite this, Hannah played a crucial role in his education. She ensured that he attended the King's School in Grantham, where he received a solid foundation in classical education. Newton's time at Grantham was marked by his early interest in mechanics and mathematics, which later blossomed into his lifelong passion for science. Isaac Newton had no siblings from his parents' marriage, but he had 3 half-siblings from his mother's second marriage, Mary, Benjamin, and Hannah Smith. His relationships with his half-siblings were not particularly close, as Newton was primarily focused on his studies and scientific pursuits. The distance created by his early separation from his mother and stepfamily contributed to his somewhat solitary nature. The complex dynamics of Newton's family life had a lasting impact on his personality and career. The sense of abandonment he experienced as a child may have contributed to his intense drive for academic success and recognition. Newton's solitary nature allowed him to devote himself entirely to his research, leading to his groundbreaking discoveries in mathematics, physics, and astronomy. Despite his strained relationship with his mother, Newton remained dutiful and caring towards her in her later years. He took responsibility for managing the family estate and ensured that his mother was well cared for until her death in 1679. This sense of duty and responsibility extended to his half-siblings as well, although his primary focus remained on his scientific work. Isaac Newton's family background and relationships played a significant role in shaping his character and career. The early loss of his father, his separation from his mother, and his complex family dynamics influenced his solitary nature and intense dedication to his studies. Despite the challenges he faced, Newton's remarkable intellect and perseverance allowed him to make revolutionary contributions to science. Understanding the family context of this extraordinary scientist provides a deeper insight into the personal experiences that shaped his life and experiences. Isaac Newton and the discovery of the law of gravity. Isaac Newton, one of the most influential scientists in history, is renowned for his groundbreaking contributions to mathematics, physics, and astronomy. Among his many achievements, the discovery of the law of gravity stands out as a pivotal moment in the history of science. The Apple Incident, a moment of inspiration. The story of Newton's discovery of the law of gravity is often associated with the famous anecdote of an apple falling from a tree. According to popular accounts, Newton was sitting in his garden in Woolsthorpe, Lincolnshire, in 1666, when he observed an apple fall to the ground. This seemingly mundane event sparked a profound realization in Newton's mind. The same force that caused the apple to fall must also govern the motion of celestial bodies. While the apple story is likely embellished, It captures the essence of Newton's ability to draw insights from everyday observations and relate them to broader natural phenomena. The falling apple prompted Newton to question why objects fall to the ground and what force governs their motion. This curiosity laid the groundwork for his revolutionary work on gravity. Newton's insights into gravity were not immediate. They were the result of years of meticulous study and mathematical reasoning. During the Great Plague of 1665 to 1666, Newton retreated to his family home in Woolsthorpe, where he engaged in a period of intense intellectual activity. During this time, he developed the foundations of calculus, conducted experiments in optics, and began formulating his theories on motion and gravity. In the early 1680s, Newton's thoughts on gravity crystallized, and he began to develop the law of universal gravitation. He proposed that every mass exerts an attractive force on every other mass, and the magnitude of this force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This relationship is expressed by the equation F equals G, frac m underscore 1 meter underscore 2, r, a, where F is the gravitational force, G is the gravitational constant, m underscore 1, and m underscore 2 are the masses of the two objects, and r is the distance between their centers of mass. Newton's law of universal gravitation provided a unified explanation for both terrestrial and celestial phenomena. It explained why objects fall to the ground, why the planets orbit the sun, and why the moon orbits the Earth. This law was instrumental in confirming the heliocentric model of the solar system and provided a mathematical basis for Kepler's laws of planetary motion. The publication of Newton's seminal work, Philosophiæ Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, in 1687 marked a turning point in the history of science. The Principia outlined Newton's laws of motion and universal gravitation, revolutionizing our understanding of the physical world. Newton's work laid the foundation for classical mechanics, which remained the dominant framework for understanding the motion of objects for over 2 centuries. The impact of Newton's discovery of the law of gravity extends far beyond his time. It provided a comprehensive explanation for a wide range of natural phenomena and paved the way for future scientists. While his work on the laws of motion and universal gravitation is perhaps the most well-known, his contributions to the field of optics are equally significant. Newton's seminal work, Opticks, published in 1704, revolutionized our understanding of light and color. This essay explores the key concepts and experiments presented in optics, the impact of Newton's work on the field of optics, and its lasting legacy. The nature of light and color. In Opticks, Newton presented a comprehensive account of his experiments and theories on the nature of light and color. One of his most famous experiments involved passing a beam of sunlight through a glass prism, which dispersed the light into a spectrum of colors. Newton observed that white light was composed of various colors, each with a different degree of refraction. This experiment demonstrated that colors are inherent properties of light, not the result of interactions with matter, as previously believed. Newton's work challenged the prevailing theory of color, which was based on the ideas of Aristotle and Descartes. According to the old theory, colors were thought to arise from modifications of white light by the interaction with materials. Newton's experiments, however, showed that colors are intrinsic to light itself, with each color corresponding to light of a specific wavelength. Opticks is divided into 3 books, each containing a series of experiments and observations. Some of the key experiments and findings presented in the work include: 1. Experiment Num Crucis, crucial experiment. Newton used a pair of prisms to demonstrate that when a beam of white light is dispersed into its constituent colors by the first prism, and then passed through a second prism, the colors remain unchanged. This experiment provided strong evidence that colors are fundamental properties of light. 2. Theory of color and light. Newton proposed that light is composed of particles or corpuscles, which travel in straight lines. He suggested that different colors of light correspond to particles with different properties, such as size and speed. This corpuscular theory of light was in contrast to the wave theory of light proposed by Christian Huygens. 3. Reflection and refraction. Newton investigated the behavior of light when it encounters different surfaces and materials. He formulated laws of reflection and refraction, which describe how light rays change direction, when they strike a surface or pass through different media. These laws are fundamental to the study of optics and remain widely used today. 4. Interference and diffraction. Although Newton did not fully develop the wave theory of light, he made important observations related to the interference and diffraction of light. He described the phenomenon of Newton's rings, a pattern of concentric circles observed when light is reflected between two surfaces. This phenomenon is now understood as a result of the interference of light waves. Optics had a profound impact on the field of optics, and laid the foundation for future research in the study of light and color. Newton's experiments and theories challenged existing beliefs, and provided a new understanding of the nature of light. His work influenced generations of scientists and researchers, including Thomas Young and James Clerk Maxwell, who further developed the wave theory of light and the electromagnetic theory of light, respectively. Newton's contributions to optics extended beyond his scientific work. His meticulous approach to experimentation and observation set new standards for scientific inquiry. Optics is not only a significant scientific treatise, but also a model of the empirical method, demonstrating the importance of careful experimentation and logical reasoning in the pursuit of knowledge. Feed Asha the elephant by subscribing. If you enjoyed this video, drop a like and comment.